So, okay. So before I start, sometimes you'll see me looking to the left is because I have a second screen where all the pictures are. So if you see me looking to the left and talking, it's because I'm looking at the pictures and the people. Okay. All right. So thank you very much for coming to my talk. I'll be talking about the fixed angle inverse scattering problem. Uh, and this is work done with uh, Lori Yuksanen from University of Helsinki and Mikko Salo from University of Jyväskylä. And I'm thankful to the NSF for partly supporting my work. Okay, so let me formulate the problem. Um, you know, it's going to seem very elementary based on who's on the attendance, but typically what we want to do is, so we have a medium, acoustic medium, which is uniform outside some ball, which I'll assume is the unit ball. And we want to determine the acoustic properties of the medium by probing it with plane waves and measuring the response, far away, or because the medium is uniform, it's equivalent to measuring it on the boundary of the ball. So the acoustic medium is going to be modeled by a Riemannian metric, Gij, which is the Euclidean metric outside the ball. And so we are going to send in a plane wave coming in from the direction of the unit vector omega. It'll interact with the medium, and the medium response will be measured on the boundary of the ball for a certain time period. And from that measurement, we would like to recover the Riemannian metric. So that's the problem mathematically. So if omega is a unit vector in Rn, then let U sub omega be the solution of the initial value problem. For this is the Laplacian G is the Laplace-Beltrami operator associated with G. And initially, the plane wave, before it hits the inhomogeneous part, it is just the heavy side h of t minus x dot omega. It's a solution of the wave equation as long as you don't hit the homogeneous part. So U sub omega is the plane wave when t is small enough. -1 is the time actually when the plane wave first hits the ball, the inhomogeneous part. So U sub omega is a solution of this initial value problem, representing the interaction with the incoming plane wave. And here, so Laplacian G is the Laplace-Beltrami operator, which is given by this form in coordinates. So here Gij is the original metric, Gi upper Ij is the inverse, absolute G is the determinant of G, and this is the Laplace-Beltrami operator. We also can consider, instead of this an anisotropic medium, we can also consider an isotropic medium, meaning at every point the velocity is given by a function. The velocity is 1 over square root rho, but it's more convenient to work with rho. So instead of this delta t square minus Laplacian G, one could instead consider rho x delta t square minus Laplacian, where rho of x is related to the speed of sound in the medium. And again, we assume that the speed of sound is 1 outside the ball. So, whatever we do actually we'll do simultaneously for the rho problem or for the Riemannian metric problem. The Riemannian metric problem is a little harder. So what we want to do is, so we have this map which takes the Riemannian metric G to the measurement value of the solution U sub omega on the boundary of the ball, and you measure it for a certain time period. Now, because we are trying to recover a function, Riemannian metric G, so it's a positive definite symmetric matrix. So it has, n plus 1 over 2 different functions in G. So one cannot expect to recover G just from a single experiment. You will need, perhaps n plus 1 over 2 different incoming directions. So that's what we do. We'll allow incoming waves which are parallel to the coordinate axis. So EI going from 1 to n, or this combination EI plus EJ over square root 2. So EI is the vector parallel to the coordinate axis. And so these are these n plus 1 to incoming wave directions. and we're going to gather data for each of these incoming directions on the boundary. So that's the forward map. And the question is FT injective? That's the question. And by the way, the fixed angle thing which we talk about, so if you're doing the row problem, then we need only one incoming direction. So that's the fixed angle in the title. Okay. For the Riemannian metric, it's still a finite number, which is dimension dependent. How many experiments we have to do? So the question is this map f of t injective? Is this enough information to distinguish between two different Riemannian metrics? Katya, can you see the last line, which is ft nonlinear and all that stuff?
Yes.
Yeah.
Yes.
Okay. All right. Thank you. So, of course, we all know this, that ft is a nonlinear map. The dependence of the solution on G is nonlinear. And, different people think, how you measure how much dependence, but in the usual sense, it's a formally determined problem. You're trying to recover a function G, which depends on n variables, x1 through xn. And your data depends on the measurements are on the boundary, that's n minus 1, and plus 1 time, that's n. So in that sense, it's formally determined. We also know that ft is not injective. If you have any diffeomorphism of Rn, which is the identity outside B, then the metric f psi star G, the pullback of G, has the same data as the metric G. So, of course, ft is not, it should be f sub t, sorry. So it's not injective, but the question is it injective up to a diffeomorphism, which is the identity outside B? So that's the question that we are interested in addressing. And so we are interested in doing it for G, and we are also interested in doing it for the rho. And I said the rho problem is easier because there's only one function to be recovered. For the G problem, we have to recover nn plus 1 over 2 functions. So let me first state the result, and then I'll do the history and then what the technique is. So the result is, of course, with Laurie and Mikko. And suppose G is a Riemannian metric on Rn, and G is the Euclidean metric outside the ball. And you collect the data on the boundary, and suppose FTG is the same data as the one coming from the Euclidean metric, and T is large enough. Then there is a diffeomorphism psi from Rn to Rn, which what it means is then G is equal to the Euclidean metric up to a diffeomorphism, which is the identity outside B, right? So it's stated this way. So that's the result. And we have a similar result for the velocity problem for the rho. We only need one experiment where rho of x is the velocity or the slowness, which is 1 outside B. And of course, everything is smooth. Everything is in the smooth thing. We also have a similar result for the boxish, the wave operator coming from a Lorentzian metric, which I will talk about in a later slide. But the Lorentzian case requires considerable more work. It's much more subtle argument, which I'll talk about in a bit. So, our result is, of course, a very small step towards proving the injectivity of F. We are just comparing G with G Euclidean, whereas we want to compare two arbitrary metrics. But the important thing is that we do not make any other assumptions about the Riemannian metric G. Associated to this, there are these solutions U sub omega. They are Lagrangian distributions, and associated to them, there is this boundary normal geodesic flow. And a lot of the work, I'll talk more about it, which can be done is under the assumption that that boundary normal geodesic flow does not have any focal points. We do not make any such assumption. And that is sort of the significant part about our result, that we do not need to make any assumptions about a metric G having, some particular flow or something not having any focal points. That's perhaps the most significant aspect of this result. Of course, there are very few results for multidimensional formally determined inverse problems for hyperbolic operators where the velocity is non-constant. Uh, so the velocity or the wave velocity in the medium is non-constant. That makes it much harder, which I'll explain again why that is so. Okay. I just want to, a lot of people work on elliptic problems, and I think it's all well known that if instead for the wave operator, if you just look at the similar problem for the Laplace-Beltrami elliptic operator and trying to recover the metric from the Dirichlet-Neumann map, then even this kind of result is not there. That is, can you distinguish the Riemannian metric from the Euclidean metric from the Dirichlet-Neumann map for the elliptic operator? So results of the type that we have are not so not so easily done, because of course, elliptic problems are much harder. But still, so these are not easy results. Okay. So now I'm going to give a partial history, and please excuse me if I mismentioning your work. There is a much more detailed history in the 2 articles that we've published. So please forgive me if I don't mention you. There's only like a limited amount of space here. So for the rho problem, the one-dimensional problem is very well understood. It's still non-trivial. And this was the work of Gelfand, Levitan, Krein, Marchenko, and many others in the 50s, 60s. And the results are really complete. They do injectivity, stability, reconstruction, range characterization, all of those things. And it's still hard, even in 1D, because of course the map is, FT is not linear. In the multidimensional case, for the rho recovery problem, the velocity recovery problem, Romanov showed, again, I'm just being a little vague here. FT is injective if rho is close to 1. So, but of course, and this is what I was saying, if rho is close to 1, then the boundary normal geodesic flow associated with the U omega has no focal points. So certain techniques are available. So this assumption rho close to 1 is important for that. But even with this assumption, even if you have this, no focal points, even then it's a difficult argument. So the result is non-trivial, even for rho close to 1. There is a similar result for the rho problem, where he does not assume rho is close to 1, but assumes that, rho, if you think of a variables x, y, z, and your incoming wave is in the z direction, then he assumes that rho has some sort of analyticity in x, comma, y, meaning there is a power series expansion in x and y. And then, you can sort of try to use ideas from the one-dimensional case. It's still very difficult. And there are some results for that case. If you want to do this problem, but instead of doing plane waves, this is an old result of Bohemian Klebanov, very important because they introduced a completely very important idea for tackling formally determined hyperbolic problems. Instead of plane waves, what they do, their sources are actually initial data. So they have this operator, but the source is the initial data at time t equal to 0 is f, and it's a bounded domain problem, and ut is 0. But and the assumption on the source is that f is always positive at every point inside B. And so this was a groundbreaking result, but it's not the kind of source we want to use, because this is like saying that we shake the whole Earth everywhere. They assume that f is positive. So initially there is a source, there's an interior source, and it's positive everywhere. So you're shaking the whole Earth. So application-wise, perhaps it's not so useful, but mathematically this was a breakthrough. Our result does not use this argument. We use a different argument. And this argument is, at least for us, it wasn't relevant at the moment. And this was the Bohemian Klebanov result is for a formally determined problem. if you go for the overdetermined problem, where you're doing on, say, a manifold with boundary and you have Dirichlet-Neumann data, then for this operator, Bereshev and Kurilev, uh, did uniqueness in the manifold sense, reconstructed the manifold and the Riemannian metric. And then, Stefanov and Ullmann in 2005 proved stability if the metric G from the Dirichlet-Neumann map is, for G is near a simple metric. So coming back to formally determined problems, if you allow constant velocity and you have lower order terms which you have to recover, again, is for the fixed angle scattering. And then even though you're recovering one Q, we need two experiment data from two opposite sides. So we proved the injectivity and stability for this problem. The velocity is constant. For the same velocity constant for recovering first order coefficients from this same kind of data, this paired solution. Ma et al. Did it in two, and this is important here. So this is for the Q problem, but with non-constant velocity, meaning for the Riemannian metric background. There is a result by Ma et al. Okay. So this is just a partial history. There are other results. The articles that we have, the two articles that we have, there's much more detail in that. So what's the result for the Lorentzian metric? So suppose we have, Rn plus 1, that's Rn times R. And suppose we have Hxt is a Lorentzian metric, which is time-oriented. And so signature is minus and plus. So one negative eigenvalue and then n positive eigenvalues. And then we're going to do a similar problem. We'll probe it with plane waves and measure the response on the boundary. So we assume that the Lorentzian metric is the Minkowski metric outside the cylinder B cross R. And then, and dt is future directed. So from the time orientation, we assume that outside dt is future directed outside. So that's the first assumption. The second assumption is now we have to formulate the forward problem, and the forward problem has to be well posed. So we need to make an assumption about the Lorentzian metric, and it has to be what's called globally hyperbolic. What that means is that there is a smooth function tau from Rn plus 1 to R called the temporal function. It's sort of like a replacement for the time. It's surjective, and d tau, so the velocity vector associated with the tangent vector associated, with the duality with d tau is future directed, and every inextendable time-like curve intersects the level surface exactly once. So being globally hyperbolic is roughly that's what it means. And this is good enough to allow the creation of the solution of the well-posed forward problem. Okay. Now, of course, we also need one other condition. We are measuring things outside, and we have to go from the outside to the inside. So we need a unique continuation result for the time-like Cauchy problem. Now, we did not need to do this explicitly for the Riemannian case because of the Tataru-Robiano unique continuation result for PDEs when the coefficients are either analytic in time or independent of time. Then there is unique continuation across every non-characteristic hypersurface. So the Riemannian case, we did not need any assumption like this. But in the Lorentzian case, because the coefficients depend on time, the Tataru-Robiano unique continuation result is not available for us. So how do we go from the outside to the inside? We have to make this assumption that if you have any solution on the cylinder and Cauchy data is 0 on the lateral boundary, for a certain time interval, it's only from R onwards, then U must be 0 in the interior over a smaller time period. So we need some way to go from the outside to the inside over some time interval, but semi-infinite time interval. So we are going to assume that our Lorentzian metric is Minkowski outside and future directed, is globally hyperbolic, and has this unique continuation property over semi-infinite intervals. Okay. And then because of once we have, say, B and A and B, if you take omega as a unit vector in Rn, and so here's another thing, right? Which, so we will, of course, like the Riemannian case, we will probe it with waves coming in different directions. But notice that our metric also depends on time. So our unknown function depends on one extra variable. So it will not be enough to just gather data of U on the boundary. That will be an underdetermined problem. So to make it a formally determined problem, we have to actually introduce another parameter S. And our sources are going to be coming from directions omega, but with a time delay S. So that gives us the extra parameter to make it a formally determined problem. Otherwise, it's an underdetermined problem. So we take a real number S, a direction omega, and then U omega S is the solution of the wave equation. And it's an incoming plane wave, but notice the time delay S. So we are sending plane waves with different time delays S and in the direction omega. And we are, of course, going to choose similarly, the incoming direction is slightly more than for the Riemannian case, a little more, but not much. And the forward map is that you take the Lorentzian metric and you look at the corresponding solution of the wave equation and you measure on the boundary, on the cylinder, and you do it for all the possible directions here, omega, and you do it for all time delays S. So for the Lorentzian metric case, we need to introduce the plane waves coming with different time intervals. And of course, we need to know whether F is injective or not. And so this is again with Laurie and Mikko. We prove that assuming H satisfies this ABC condition, then if the data for H agrees with the data for the Minkowski metric, the standard wave operator, then H is equal to the Minkowski metric up to a diffeomorphism, which is the identity outside that cylinder. So it's similar to the Riemannian case, a result, except, it depends on time. And notice that our H is non-homogeneous on an infinite dimensional domain. So this takes more work to do. Regarding this unique continuation condition, I would like to mention one thing. So for example, if you take a H a Lorentzian metric, and if for large time, H is really the Euclidean metric. Not Euclidean, sorry, it's the Riemannian metric, which is independent of time, then this has the unique continuation property. Meaning, so from time beyond something, if your Lorentzian metric has this property, then C holds automatically. Okay, so that is the result for the Lorentzian metric case. So I'm just checking the time. Okay. Okay, so I will give you some idea of the proof of the Riemannian result. The Lorentzian result requires more subtle arguments. So just to remind you of the Riemannian result. So we have a Riemannian metric G on the Rn, and G is Euclidean outside the ball. And we probe it by a plane wave coming from the direction omega. So U omega is the solution of this wave equation. And this is the initial incoming plane wave. And we measure the response of U omega on the boundary of the cylinder for a certain finite time period. And for these directions omega, these n plus 1 over 2 directions omega. And we showed that if the G and the G Euclidean have the same data on the boundary for these directions, and T is large enough, then G is equal to the Euclidean metric up to a diffeomorphism, which is the identity outside B. So I'll talk a little about the arguments we used. So if you have the Riemannian metric G, we can identify the T star Rn with TRN, and that's what we will do. So the null bicharacteristics of this wave operator for the Riemannian metric G can be shown to be identified with the time parameterized unit speed geodesics for this Riemannian metric G. And the bicharacteristics, the direction in the bicharacteristics associated with the velocities of these geodesics. So we'll always make that identification. So also, if you have a function alpha on Rn, then the one form d alpha can be identified with a vector field associated coming from this Riemannian metric G, and that's the relationship. So we'll make this identification. Okay. So the solution U omega that we've constructed is actually in general it's a Lagrangian distribution. So it's got a complicated structure. It's a Lagrangian distribution associated with a Lagrangian manifold, which sits in T star Rn. And this Lagrangian manifold is generated by this boundary normal geodesics flow. So sigma minus is this plane x dot omega equals -1, and this is just in Rn. So what the flow is defined as follows. Okay, so the plane waves are coming in. So they come in, they hit this plane x dot omega equals -1. So each of those rays hits it at some point A, and then you follow the geodesic, which starts at A, and whose velocity is perpendicular to this plane. So its velocity is omega. And so it'll trace out something like that. Okay, and you do this for every point A on this plane x dot omega -1. So you have this boundary normal flow of geodesics, which is a map from this hyperplane times R to Rn, where phi of AT is the geodesic, is the position of the geodesic at time t, where A is a point on this hyperplane x dot omega equals -1 and t is R. And this is the geodesic starting at A with velocity omega, which means perpendicular. Okay, so the Lagrangian manifold associated with the solution U omega is actually coming from these, these geodesics this is the plane wave, so comes in a straight line parallel to omega, follows the geodesics, and it is happening for every this geodesic coming like this and changing. So this Lagrangian manifold that comes is associated with this phi omega. This boundary normal flow phi omega is critical to describe the solution U omega. If this map phi omega is a diffeomorphism, then the Eikenel equation Laplacian G alpha omega equals 1 has a global solution. So if this flow is a diffeomorphism, then the Eikenel equation has a global solution, which is alpha is equal to x dot omega, as if it's like the plane wave outside omega. But inside what alpha is, it's not clear. Okay, but this happens only when phi of omega is a diffeomorphism. And when this happens, then U omega has a really nice form. You can write it in this progressing wave form. It's just some smooth function, which is actually solution of the same wave equation, times Heaviside T minus alpha omega. This is the solution of the Eikenel equation. But if you don't have phi sub omega is a diffeomorphism, then the solution U omega is very complicated in its Lagrangian distribution. It's very hard to do estimates with that. But if it has this nice form, then you don't have to work with U omega with this singular thing. You can just work with this smooth part, U sub omega. So this phi omega being a diffeomorphism is very important. But we have not assumed anything about a G which guarantees that phi sub omega is a diffeomorphism. So we did not make that assumption. And that is the important point for this, that our result does not require us to assume that phi sub omega is a diffeomorphism. And the advantage is when it is a diffeomorphism, these things happen. Okay, and so this point will come up again. So So the main step on the proofs there are two main steps, okay? So just in the beginning, of course, if you show that G and G Euclidean have the same data, which means, they agree on the boundary of the cylinder, then actually you can show that the solutions agree for the Euclidean and G agree at any point outside the cylinder. It's a very elementary argument. It's just for the wave operator because G is Euclidean outside the cylinder. So a very elementary argument shows that actually U sub omega is really the just ht minus x dot omega outside the cylinder. So we'll start with this, and then, the proof has two parts to it. So there is a geometrical and a topological argument which shows that, oh, sorry, okay, I forgot to say this. Right, sorry, okay, yeah. So I call this the exterior property, that U sub omega is equal to ht minus x dot omega for all xt outside B crowns R. Okay. So this is the first part, which shows that there's a geometrical and topological argument which shows that if this is true, this exterior property is true, that U omega is just ht minus x dot omega outside the cylinder, then the phi omega must be a diffeomorphism. Okay, so this is the, if you like, the unusual part, that we show that diffeomorphism property follows from the data being equal, from the data. So U omega equals ht minus x dot omega outside the cylinder implies that phi sub omega is a diffeomorphism. So what is happening outside the cylinder allows us to say something about the geometry inside the cylinder. Okay, so that's where a geometrical and topological part is needed. Okay, and once we have shown this, then of course there is a global solution of the eigenvalue equation, and the U omega has a nice form. So this is the first part, show that phi omega, this exterior property implies that phi omega is a diffeomorphism. And that allows us to write the U omega in this nice form. Okay, and then we start with this nice form, and we have these solutions of the eigenvalue equation, one for each of the directions that we have used. And so we define this map psi from Rn to Rn, which is take the solutions of the eigenvalue equation for each of the directions, alpha E1 through alpha En. And this is and notice that, because of our assumption about this, psi of x is outside B. Then using a PD type argument for this nice form, using this nice form, now that we know we have that, and this exterior property, one can show that psi is a diffeomorphism. And it's psi is a diffeomorphism, and psi prime is an orthogonal matrix with respect to this Riemannian metric G. And that is enough to prove that G is psi star of the Euclid. G is equal to the Euclidean metric up to a diffeomorphism, the diffeomorphism being psi. So the diffeomorphism is constructed by using these global solutions of the eigenvalue equation. Okay, and we know these global solutions exist from the first argument in the first part, a geometrical and topological argument, that if U omega is equal to the heavy side T minus x dot omega outside the cylinder, then this geometry, the phi omega is a diffeomorphism. So this is sort of, for us, or at least for me, this was unusual. I've never used geometry and topology, PD inverse problem proof before. So, but this was important for us because this allows us to write the solution U omega equals this. And now we can apply PD arguments to U sub omega. Okay, before that, if it just said it's a Lagrangian distribution, very hard to work with that and prove estimates, especially for uniqueness for the inverse problem. So this argument allows us to be simplified. So there are two parts to the argument. And so, to prove so it seems like, at the moment, it seems like I did not use data from the other direction, just E1 through En, but actually to prove the orthogonality. So there is a argument which requires using the data from the other directions. So we need, this is where we use the data from the other directions to prove that psi prime is an orthogonal matrix. Okay. And So other interesting thing is actually the argument in the first part is fairly general that, here we were comparing the data for G to the data for the Euclidean metric. Actually, the argument works for more general things. Suppose you have data for two metrics, G and G1. And suppose G1 is not Euclidean, but the phi omega for the G1 is a diffeomorphism. So you're comparing two metrics G and G1. And if the data for the phi is a diffeomorphism for G1 and the data agree, then the phi for the G will also be a diffeomorphism. Okay, so this result is fairly general. It doesn't have to be compared to the Euclidean metric. This part here, if the data for G and G1 agree, and G1 has this diffeomorphism property, then G will also have the diffeomorphism property. So it's a more general result, not just for the Euclidean case. Okay, so again, it's an issue about how can you get in, how does information outside the ball give you geometrical information inside the ball about the geodesics? Okay, that's what this first part is. The second part is more specific to the Euclidean metric, that you're comparing G to the Euclidean metric. And it's for a very simple reason that in the Euclidean case, the solution is just the Heaviside T minus x dot omega, u omega. And there is this one. So this little u is actually one in the Euclidean case. And we use the fact that this one is a solution of Laplacian G is 1 is 0. This is true for any Riemannian metric. So we do use this fact very importantly. And then this is the one in the Euclidean case, the little u is 1. And that this one, you can actually use it for any Riemannian metric. So this part, the second part of the argument, is very specific to comparing to the Euclidean case. Okay, but the first part is more geometrical. It's for more general. Okay, so I'm going to talk a bit about the argument in the first part, the geometrical and the topological argument. How is it that information from the outside the ball about the geodesics, about some geodesics, gives us information about the metric inside the ball, meaning proving that the phi is a diffeomorphism. So let me remind you about what that map is. So, sigma minus is that hyperplane, which is when the plane waves come. This is the first thing they will hit. X dot omega is -1. And so this is the map phi omega, which I constructed. So from every point A on this hyperplane, you look at the geodesics, which are normal to this hyperplane, and we have velocity 1. So you're looking at gamma A0 is A, and gamma dot A0 is omega. And so you're looking at this map phi, which is the boundary normal flow with the geodesics, all with speed 1. And the question is, when is this going to be a diffeomorphism? Right? How do you show it's a diffeomorphism in a certain case? So now, because of the exterior property, u omega is equal to the Heaviside function outside the ball, which means their wave fronts will be the same. Now, wave fronts, that's in the cotangent bundle. And so when you do the identification with the tangent bundle, it's equivalent to saying that once the waves hit this, or these geodesics gamma A, the moment they're outside the ball, the velocity is omega. That's what the wavefront information says. You send in things, these geodesics going in the direction omega, go inside, do all kinds of strange things. But when they come out, because the wavefronts are the same, they must be parallel to omega. So that's the exterior property, and from the wavefront set. So whenever so it means that whenever these geodesics which are coming from this boundary normal flow, at every point outside B, they have velocity omega. That's number one. And secondly, because the wavefront set is there, through every point outside the ball, one of these geodesics does pass through. Both, so there are two things going on. These geodesics, these boundary normal geodesics, once they come out of B, they're parallel to omega and have speed 1 actually. And secondly, through every point outside the ball, there is one of these geodesics. So we have two pieces of geometrical information. And this is actually enough to prove that this phi sub omega that we have constructed is actually a diffeomorphism. So meaning the behavior inside is nice. Geodesics inside cannot cross. There are no focal points. All these things we can show. And I'll talk about that a little bit. So it's sort of interesting and perhaps surprising, perhaps not, that knowing the behavior of these boundary normal geodesics outside tells you what's going on inside the thing. Okay. And so this is the picture now. So here is the geodesic. If it starts here, it just goes straight through. If it comes parallel to omega, goes in, but the moment it comes out, it's parallel to omega. And like this. And there is one of these geodesics through every point outside B. No, so this does not preclude some trapped geodesics, by the way. Right? Maybe there is a geodesic, it never comes out. So it is possible. So we have to show that these things do not happen, that you do not have crossing things like that there are no focal points inside. And it should be just a consequence of the fact that geodesics, when they come out parallel to omega, number one. And number two, through every point outside B, there is one of these boundary normal geodesics. So how does that argument work? So there is an intermediate result which we study. So one of the things we want to show is, that, there are no trap rays. That is important for us. So what we do is, so here are these, this is the plane, hyperplane x dot omega equals -1. Things are going from there and they're crossing sigma plus. Okay. Now, because of the way, as I said, every point outside B, there is a unique boundary normal geodesic, which means through every point of the sigma plus, which is the hyperplane x dot omega equals 1, through every point of sigma plus, there is a unique boundary normal geodesic. So these boundary normal geodesics, through every point of that, there is a unique, through every point of sigma plus, there is a unique boundary normal geodesic. And of course, these things are all parallel to omega when they come out. So this allows us to define a backward map, a map from sigma plus to, so I'm trying to show that there are no trapped rays. That's what I'm trying to show, that everything will leave. So you define this backward map through every point of sigma plus. Well, there is a boundary normal geodesic on sigma minus. So you can define the map, it sends x on sigma plus to the place where, so like D will go to A, C will go to B, and this point will go to that. So we're defining this backward map, F. Okay, we trace it back to where it started from. And notice that these geodesics are transversal. So there is an implicit function argument and transversality imply that this map F, this backward map from sigma plus to sigma minus, is a smooth map, and that the range of this map, backward map M, is actually an open subset of this hyperplane. There may be trapped geodesics, we don't know. So meaning there may be some points of sigma minus which are not in the range of F. Okay, and because of the transversality, so F is a map from actually sigma plus to M, not sigma minus now. And then F inverse is actually smooth, all because of transversality and so on. So we have that the range of this backward map M is actually diffeomorphic to sigma plus. Okay. So meaning all the points where the rays are not trapped, everything which is going through that, those are the points in M, which is in sigma minus. That's actually diffeomorphic to sigma plus. Okay, so we can show that by the geometry. Okay, but what is the what kind of set is M? So if you notice that everything above this line, that's in the range, that's in M. Everything below this line is in M. This is actually the exterior of a ball. So the exterior of some ball in sigma minus is in M. Okay. Now M is diffeomorphic to this sigma plus, which is like Rn minus 1. So you have something. So question is, are there any holes in M? Right? And if there were any holes in M, remember that the exterior of a ball is sitting in M. So if there are any holes, so there are these holes in this finite region. And it cannot be diffeomorphic to Rn minus 1. The homologies will be wrong. If you have one hole in M and you have all of this thing outside, which is part of M, that is not possible for it to be diffeomorphic to Rs minus 1. So M cannot have any holes, which means that M is the whole of sigma minus 1. So homology implies that actually M is actually sigma minus 1, which means there are no traptories. Okay, so hence, if you start from this, everything crosses sigma plus exactly once, and it is the shortest path from sigma minus to sigma plus from that point. Okay. So this is, as I said, this shows that, how we can use information outside to say something about what's going on inside by a sort of a topological argument. Okay. So now that we have that, okay, everything from sigma minus must cross sigma plus and cross it at a unique point. And every point in sigma plus has something coming, and there's a unique one. Okay. So now can we show that this map from sigma minus into Rn, okay, is that a diffeomorphism, right? So which means, can you prove it's injective? Can you prove it's surjective? And can you prove that there are no focal points? So which time do we have? Okay. So let's do the surjectivity is fairly straightforward. Like, let's say there is a point, which I'm drawing, say C, then why is there actually a geodesic, boundary normal geodesic going through C? And that is because, because in the Riemannian case, we can do the Riemannian distance of C from the hyperplane sigma minus. And so they'll, by doing all the curves from sigma minus to C. So they'll be, so this is the, from the theory of Riemannian geometry, there is a shortest distance between C and sigma minus 1. And you can argue that that will be a geodesic, and that geodesic will be normal to sigma minus 1. So through every point C in B, there is actually a boundary normal geodesic, that by just a simple Riemannian geometry argument. So which shows that the map phi that we are constructing is actually surjective. Why is it injective? There's again a very simple geometrical argument. Suppose there were two boundary normal flows, like from A and from B. They both go through the point C. Okay. Now, so what about the lengths of BC and AC? Say if BC was shorter than AC, then the path BC to CE would be shorter than the shortest geodesic A to E. So that cannot happen, which means BC and AC would have the same length. But then that would mean the paths BCE and ACE, they both are the shortest distance from E to the line. Okay. But we know there is only one shortest geodesic. So that means they're both geodesics then. And that means that they're both, so we can take AC to CD, and that will be the shortest path. And shortest have to be geodesic and have to be smooth. So there is smoothness at C for AC to CD, which means both these trajectories have the same velocity at C. So they must be identical geodesics. So it's a very simple geometrical argument, Riemannian geometry argument, to show that they cannot cross. Okay. And a similar argument is that if there is a focal point, let's say at G, and then there is a theorem, one can look it up in Euclid, O'Neill's book, that if there is a focal point G, and G is on this geodesic, then if you look at a point H later in the geodesic, there'll be a shorter path from sigma minus to H than this green path. Okay. And then that again violates what we have. So these types of arguments are able to show that the phi is a diffeomorphism. Okay, so it's not a very complicated argument. The topological part was that showing that there are no trapped rays. So that was the topology part. So this shows that phi sub omega is a local diffeomorphism, this focal point argument. So it's phi omega is a bijection and it's a local diffeomorphism, so it's a diffeomorphism. So this completes the proof of the geometry and topology part of the Riemannian case. The Lorentzian case is more complicated. Firstly, Lorentzian case, we don't have the shortest distance thing. So we cannot use some of these arguments which I was using here. So the Lorentzian proof is more difficult, no shortest distance, so you need much more subtle geometrical arguments. We have to do, And the other thing is that H is inhomogeneous on this cylinder, which is infinite. So that homology argument I gave you, that will not work. And that has to be replaced by some Hadamard's theorem, which says that if you have any smooth map from Rm to Rm, which is a local diffeomorphism and proper, then F is actually a diffeomorphism, which means it's injective, surjective, and so on. It's a very surprising result. I mean, it's an old result that local diffeomorphism and being proper is good enough to prove injectivity and surjectivity. That's the so we have to replace the homology argument by this argument, and we have to do more subtle things for the Lorentzian case. So that's it, and thank you. Thanks very much.
Thank you very much, Rakesh, for the very nice talk. Thank you so much. Are there any questions or comments, please? Please feel free to unmute yourself. Any questions or comments, please?
Hopefully I didn't go too fast. I'm not sure how fast I was going.
Okay, let me ask a question.
Please, Clement.
Okay, at what point did you use unique continuation? I missed that.
Okay, so it's, let's see. Yeah, the unique continuation came to play in the second part. The part which I did not talk about. So there were these two parts. And I'll tell you, let's see. I'll tell you where we use it. Okay, so from the first part, we get that, U omega has this form, right? And then, and now U sub omega is equal to 1 outside the cylinder. So we look at the U omega minus 1 is 0 on the boundary, and normal derivative is 0 on the boundary. And U omega minus 1, and because 1 satisfies also this, so Laplacian G of U omega minus 1 is 0 in the cylinder. And so the unique continuation argument says that little U omega minus 1 is 0 above this characteristic surface. So that's where we use the unique continuation. And we don't need to assume it because Tataru's unique continuation result works. So that means I know that little U omega is 1 above the characteristic surface. So this turns out to be 1 above the characteristic surface. And once you do that, and it's a solution of the wave equation, which actually shows that the alpha E1s are solutions of Laplace G of alpha is 0. So each of these alphas, not only the solutions of the eikonal equation, they're actually solutions of Laplace's equation. Laplace G equals alpha equal to 0 on Rn. And alpha is equal to x dot omega outside the ball. So
Yes,
did I make myself clear?
Well, I still need to look at the paper to get all the details, but that U omega, which is the coefficient in front of H, I mean, in principle, that is defined by geometric optics only on the support of H, right? So
right, the principal part is, but omega itself is a solution of actually the wave equation above the characteristic surface. And its value on the characteristic surface is given by geometric optics.
Okay.
So it's what is that? So U omega is what's called the solution of the Goursat problem. You prescribe U on the characteristic, and it satisfies the wave equation above it.
Yeah, okay, thank you.
Thank you very much. Are there any other questions or comments, please?
Yes.
Please.
Go ahead.
Hi, Rakesh. Yes,
Hi.
wonderful talk. You explained this very well. I just have a little question here. Once you have all the geodesics, so to speak, entangled, can you also say, for instance, that the Riemannian distance function originating at any point would be convex?
Okay. I haven't thought about it. I don't know. I think Mikko is here. Maybe he's thought about it. Mikko, do you have anything to say about Matthias's question?
Not really.
Okay, all right. We haven't thought about that. Yeah, so okay. Which means, so you're asking, so let me see, okay. So I guess your question is really about the more general thing. That suppose, because I claim, right, the first part is true for more general situations. Right? That if you have the data for two different Riemannian metrics, and they're the same, and one Riemannian metric satisfies the diffeomorphism condition, which I'm talking about, then we've shown that the second Riemannian metric also satisfies the diffeomorphism condition. So my second question, your question, I guess, would be if the first Riemannian metric, there are convex functions for it, does the second Riemannian metric also have convex functions? Is that your question?
Yeah, kind of. I mean, so,
yeah, I don't know that. That's actually a very interesting question for some other things we are trying. So yeah, it's existence of convex functions. I mean, I know very little. My differential geometry is very weak, but Mikko has some things, but I believe it's not that well, maybe it's well understood. I don't know. Yeah, but that's important for, doing Carleman estimates and things. We did not need Carleman estimates for this because we were comparing it to the Euclidean metric. So we didn't use any Carleman estimate, just the unique continuation result of Tataru and Rubiano, just to go in. But when you're comparing two different Riemannian metrics, I think we'll need Carleman estimates and the Bugin-Klimanov method and so
on. Okay, thank you.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? If not, thank you very much, Rakesh, for the very nice talk. Thank you so much. Thank you very much, everyone, for coming. Thank you.